Welcome back to Calculus 1. In this lecture, we'll introduce two of the most useful ways to calculate derivatives with two rules called the Product and Quotient Rules. Okay, so let's get started. I will say, probably for those of you continuing through the calculus sequence, for some of the content from our course that you will continue to use, right now, the product and quotient rules are probably some of the most essential things to take away from our course. Now, these are just going to be rules for calculating derivatives, just one aspect of calculus. But if you are continuing, these will be continued to be used all the way through the rest of the calc sequence, even up through calc 27. Okay, let's go ahead and get started. Let's start with two simple questions here. Finding the derivative of the function x squared times e to the x, and then the other function here, the derivative, we're looking for the derivative of the function x squared minus 1 divided by x squared plus 1. Now, the first example there, we're asked to find the derivative of a product, and then the second one, we're finding the derivative of a quotient or fraction. Now, unfortunately, the rules of math don't work as you might like. So unfortunately, for that example, the derivative of x squared times e to the x, we can't just differentiate each factor. While the derivative of x squared is simple, 2x, the derivative of e to the x is also simple, e to the x. The derivative of x squared times e to the x is not just the product of their derivatives. Unfortunately, it's just not true. We'll take a look at a specific example to see why, but it's a very common misconception. This is not the correct statement for the product rule. And similarly over there, for the derivative of a quotient, it's not just as simple as differentiating the numerator and then differentiating the denominator. Okay, so if these are not the right rules for the derivative of a product, f times g, or the derivative of a quotient, f divided by g, what are the correct rules? Well, we need to state these two new differentiation rules, and they're named uncreatively. For products, we have something called the product rule. And then for quotients, any guesses? We have something called the quotient rule. Okay, at this point, there's really nothing else to do other than just state what these new rules are. Now, I will admit, these are very deceptive for students. They look really simple. They're simple to memorize. It takes a lot of work to really understand how they're used in practice. So as you start going through homework problems for this lecture, make sure you do a lot of problems. There's only a handful of examples we have time for in class within the recorded lecture, but there's a huge variety of different looking problems that you could be asked to answer within homework and other calculus resources. So make sure you put time in to really understand how this is used, the product and quotient rules. It's not as simple as just memorizing their formulas, which we will get to right now. So let's start first with the product rule. At any point, definitely pause to make sure you take detailed notes for this. This is stated in every calculus textbook, but you should also have it in your notes with you wherever you do your homework questions for reference. And it starts off by us trying to find the derivative of a function, f of x times g of x. That's fairly standard notation for calculus courses. Our function is a product of two other functions. We call those two other products f of x and g of x. Okay, and what we have stated down here, if that is our function, the derivative of that product, what we call the product rule, if we read it kind of going left to right across there, it's the derivative of f of x times g of x plus f of x times the derivative of g of x. Okay, again, the formula looks simple. Notice on the left, we're differentiating, written in Leibniz notation, as f of x times g of x. And the way the product rule works is we basically differentiate one factor at a time and then multiply by the other function. We might kind of reword this statement of the product rule, the way it looks, f of x is the first function going left to right, and g of x is the second function. So you might hear us sometimes say informally or in class for us within the recorded lecture, the product rule could be reworded as it's the derivative of the first function times the second function, and then we add to that the first function times the derivative of the second function. Again, first function is f of x, second function, g of x. Now, there's nothing wrong with this notation, with Leibniz notation, other than it's just really not convenient to write by hand when you're going through lengthy calculations. So let's kind of shorten this a little bit with two other versions. Instead of expressing a derivative in differential Leibniz notation, d over dx, we can write it also as prime. So these are all equivalent statements for the product rule. Pause, make sure you copy all three down. As we go through examples, just to keep it brief, like I would in class, we're usually going to refer to the product rule in the the last version stated there. The derivative of f times g, where f and g are both functions, is f prime times g plus f times g prime. And that's a little shorter in terms of notation, suppressing the function of x notation. Just make sure you realize with that third version down there, both f and g are functions of x. Okay, now if you haven't paused to copy these down, definitely do so. I'll give you a few seconds. All right, and we'll take a look at kind of why the product rule can't be the version that we want, just simply differentiating each factor. So let's kind of pause to state an important idea, a very common misconception of what the product rule is. The derivative of f times g is not f prime times g prime. All right, now, again, in a mathematics course, it's one thing to be told that. Let's take a look at a specific example to see why this is false, why that can't be the correct version for the product rule. Okay, so let's keep it informal. We'll write derivatives in prime notation. Suppose I ask you, what is the derivative of x squared? Power rule gives it just as 2x. So this is correct. Now what we want to do is let's rewrite x squared as a product to see why that kind of statement there for the product rule, why that has to be false. So let's rewrite x squared as x times x. Now, if we differentiate x squared that way, thinking of x squared as x times x, let's suppose we try that incorrect statement of the product rule. If you differentiate each factor, differentiate x, and multiply that by the other derivative of x, each derivative of x, the derivative of x just by itself, x to the first power, is just 1. Now we know the derivative of x squared has to be 2x, but this incorrect version for the product rule gives the derivative of x squared as 1, which we know is not true. Hopefully this gives you some idea of why, right next to important there, why that is definitely not the correct version for the product rule, why that statement is false, written as not equals there. Okay, when you're ready, we are going to jump into stating the quotient rule in similar notation, and then we'll close this part of the lecture, this is part 1, with a bunch of examples. All right, when you're ready, let's advance to the quotient rule. Okay, the only difference here is our function, while it's a combination of two functions, f of x and g of x, instead of multiplying, we divide them. And in mathematics, the technical term for dividing, we call that a quotient. So here we could call this the fraction rule, but we'll be technical and call it the quotient rule. For finding the derivative of a function that is a quotient of functions. Okay, now I'm going to state the version here first in Leibniz notation. This is probably usually the first version stated in a standard calculus course. And it's a little bit different than what you might find in the textbook and in other resources. Now, it's a more complicated formula. Notice f of x we're going to refer to that as our numerator from the function. G of x will denote the denominator, or the function in the denominator. The formula for the quotient rule has g of x, the function's denominator, squared. All right, and the numerator of that end result for the quotient rule is sufficiently complicated. Now, again, the version I have stated here is a little different than what's stated probably in a calculus textbook or other resources. The reason for that, the version I like here, is as long as you know the product rule, this statement looks very similar. So I always, in class, just as a quick mental check, and it looks like it's seamless, but I always pause very briefly in my mind to think of this, is my numerator for the quotient rule correct? And I always ask myself, it's basically the product rule, but instead of a plus between, there's a minus. So this is a kind of just a neat little short trick to make sure you have the correct version for the numerator here in the quotient rule. Remember it as being basically the product rule, but with a minus between instead of a plus. Why I'm mentioning that, with the product rule, there's an addition between the terms. Order does not matter with respect to addition. Here, notice that subtraction sign in the numerator. If you were to flip the order of subtraction, then you would get a different result. So order does not matter for addition, but order does matter for subtraction. Now, there's lots of ways to keep track of this. There's versions calling f of x the high function, g of x the low function. A lot of different versions, which are all just different ways to memorize this. This trick with the numerator being the product rule with a minus is just one of several, a myriad ways to memorize the quotient rule. All right, so again, pause, make sure you have this in your notes. We're going to take a look at the alternate versions that are a little more compact in terms of notation. Moving forward to examples, when we apply the quotient rule, I'm probably going to use this version right down here without the function of x notation. So keep in mind here, f and g, they're denoting functions of x. F is going to refer to our numerator of our original function, and g will refer to the denominator of our original function. Okay, now it might be helpful to see these both side by side. So let's advance one more slide just to see what the product and quotient rules look like together in their kind of most compact form and notation. All right, so definitely pause, write these down, have these in front of you before we advance to the next two examples. Example 1 and 2 are going to be multi-parts each. Example 1 will deal with the product rule. Example 2 will deal with the quotient rule. When you're ready, let's get to our first set of examples. All right, let's advance to example 1. All right, so the question is really simple. Find the derivative of each function. Now, we've started in the last lecture answering that with basic rules, the derivative of a constant, the derivative of a power, and then the derivative of an exponential function. And basically from the last lecture, this lecture, and the next few, we're going to be looking at kind of different functions and how we might differentiate them. So basically for the next few lectures, we'll be seeing this question come back, but for different functions. Shortly, we'll be getting to every calculus student's favorite type of functions, trig functions. But let's get through this lecture first. Okay, so let's go through part A together. I want to go through one that's really simple and point out a very useful problem-solving technique in mathematics, or just in general, a very useful problem-solving technique. And it's what might be known, what I call divide and conquer. And basically what this is a way to take a problem, any sort of problem. For us, it's going to be a mathematics problem. And the dividing part refers to splitting the problem into several simpler problems. And the thought is take a big, complicated problem, split it into multiple, several simpler problems, solve the simpler problems, and then combine them back together, thus conquering solving your problem, the original complicated one. Okay, now how does this work here for what we'll refer to going through examples, what I refer to as divide and conquer? Well, first we're going to want to identify the appropriate f and g, f of x and g of x. Now, if we take a look at our function here in part A, h of x is a product. We're multiplying x squared by e to the x. So our first step, identify f and g. From the product rule, they're just the two factors. So we can say f of x is x squared, and then g of x is e to the x. Okay, pretty simple. Again, divide and conquer basically just breaks one problem down into several simpler problems. So this is pretty simple. F and g are just the two factors. All right, the second step would be we want to calculate the individual derivatives. And this is where the work occurs. We're going to use our previous differentiation rules, all combination of them so far. Usually the power rule, and then so far the derivative of an exponential function. So if that's our f and g, maybe pause the video, give yourself a few seconds to calculate those two derivatives, f prime of x and g prime of x. Should be really simple. All right, and you should get these results. You should get f prime as 2x, applying the power rule, and g of x, an exponential function, e to the x, well, its derivative is the same thing, e to the x. So g prime is e to the x. Okay, so step one is simple, step two is simple. How we solve the problem is we just combine the pieces back together. Now we're going to be using this notation, f and g, a lot. We already used f and g to denote the two factors. And with the quotient rule, f and g refer to the numerator and denominator respectively. You have to keep track of what your f and g refer to. So divide and conquer is a very general method, but it's not foolproof. Very easy to get confused with how you recombine those four pieces, f, g, f prime, and g prime. Now our function was identified as a product, so we combine those four pieces, f, g, f prime, and g prime. We combine them in this pattern with the product rule. So at this point, it's just plugging in our work off the left there, right into the formula for the product rule. All the derivatives are calculated already. Now we just combine them back together, conquering our problem. Okay, so we just combine them together. Just make sure you're comfortable with that. I have the terms underlined. 2x is f prime, g of x is e to the x squared is f of x, and g prime is e to the x. Okay, and that is basically it. Okay, now this, as it turns out, can be simplified. There is some expectation at this point in our course, Calculus 1. Not only do we calculate derivatives, but you definitely want to simplify them. And the reason for that is we did allude to earlier briefly kind of the need to calculate higher order derivatives, derivatives of derivatives. Within a lecture or two, we'll be getting to position, velocity, and acceleration questions, where we'll have to calculate typically up to a second order derivative. Now, we want to simplify this. Notice this is h prime. There will be some questions where we're asked to calculate a second derivative, h double prime. Now, we wouldn't want to leave our answer in this form. Notice how many products we have. The first term, 2x times e to the x, is a product. The second term, x squared times e to the x, is again a product. So if we were differentiating h prime, so calculating a second order derivative, we would have to use the product rule twice here as written. Well, we can simplify this. Notice each of those terms there contains a factor of e to the x. And exponential functions are fairly important throughout calculus. We're going to see them scattered through a lot of examples. So it'll be very common for us to get a derivative like this end result here, and then factor e to the x out from each term. Okay, so we get this kind of simplified derivative, a factor 2x plus x squared, and then what we factored out times e to the x. And this, I'm going to say, is the best version when we go on to calculating higher order derivatives. Now, you might be arguing, and you are correct, that this could be simplified even further. Notice in parentheses, 2x and x squared have a common factor of x. And you can factor that out, writing your answer as this last version, x times 2 plus x times e to the x. This is fully factored, but it's not going to be useful for finding h double prime. The reason for that, and we will get to that within a second part of this lecture, notice that version has 3 factors. The product rule, as we've stated it, only applies when the function has 2 factors. Now, it is possible to iterate, apply the product rule several times, but who wants to do that? You guys want to kind of get through the problems in the quickest, most efficient way. And I'm going to kind of claim that the version there in the middle, where we only have factored out e to the x, that's the best version. The original version, unfactored, not efficient, because we have to apply the product rule twice. The last version, fully factored, has 3 factors. We haven't applied the product rule to 3 factors yet, but the middle version is just right. We'll see that within an example in part 2 of this lecture. All right, now hopefully that wasn't too much information, but I do try to give details as relevant when they pop up for questions where we're going. All right, let's take a look at part B, which is an interesting example. In case you haven't attempted it yet, maybe not feeling sure how the product rule works, maybe re-pause here and give yourself an attempt. So definitely pause, retry this. This one we're going to look at solving it in 2 ways. We'll check in several minutes. All right, I'm going to assume you made an attempt. We'll start with the maybe obvious way. This is written as a product, so we can, of course, use the product rule. But I'm going to argue you probably don't want to use the product rule here, but we can. We'll take a look at a follow-up, what I mean by that, why you wouldn't want to apply the product rule. I mean, that's what we're learning about, but recall earlier in a few spots we mentioned the idea of rewriting first. We'll see that in action as a second way to solve this. So for our first attempt, let's solve this using the product rule. Okay, that is completely correct to do that. The function is expressed as a product. It's factored. Our f of x is 3x squared plus 1. Our g of x is 2x plus 1. Finding these individual derivatives really simple. So we've divided the problem into simple pieces. Again, this is divide and conquer, not the mathematical operation of division. So we split the problem into simpler pieces. The individual derivatives here for f prime come out to 6x. And then for g of x, its derivative g prime is 2. Okay, and that is pretty much most of the work. The rest of it is just combining these pieces with the product rule. F prime times g plus f times g prime. Okay, the calculus is done. Now we can simplify this answer. Notice you can just kind of distribute through the parentheses. And then you have some like terms that you can combine together. The x squareds can be combined, and you get a kind of a simplified version, 18x squared plus 6x plus 2. Okay, so the product rule works here. It seems pretty efficient. But what if I told you you could solve this problem without using the product rule at all? Now, this applies here. There's going to be plenty of other examples where this next idea is kind of essential. Rewrite your function before you even do any calculus. So rewrite your function before applying the product rule or before applying the quotient rule. And notice here, instead of multiplying kind of after we've found our derivative, notice right in the middle of the page, we multiply it out, y prime. Well, why not just multiply out from the beginning? And that avoids bypasses using the product rule. If you multiply that out, you'll get 6x cubed plus 3x squared plus 2x plus 1. And now that's pretty effortless to calculate the derivative. That's just going back to our previous lecture when we combine a combination of the constant multiple rule, the power rule, and then the sum difference rule. So in that simplified version, calculate your derivative and you get the same thing. I think the work looks less, so this maybe seems simpler. Again, this is a fairly important problem-solving technique in calculus for finding derivatives. Maybe rewrite your function and you can have a more efficient way to calculate the derivative. All right, when you're ready, we'll take a look at example 2, which is on applying the quotient rule. Okay, now I feel somewhat confident that some of you get the hang of how divide and conquer works for the product rule. You can also apply divide and conquer for the quotient rule. Notice here in example 2, both functions in part A and B are quotients, they're fractions. So if you feel like you get the product rule, give yourself a chance to try divide and conquer. The only new part is identifying f and g as numerator and denominator, respectively, and then combining them back together with the quotient rule. If you feel comfortable, pause, give this an attempt. Otherwise, we'll just continue. I'll give you a few seconds in case you want to pause. Okay, let's go through this. Either you made an attempt or you just want to kind of work through this together. That is okay if you want to. This is new. This is our first time applying the quotient rule after all. All right, so we're going to identify our pieces. F is the numerator. G is the denominator. So f of x is 2x minus 3. G of x is 3x plus 2. And individually, those two derivatives, f prime and g prime, are really simple. 2 and then 3. All right, the only work left is step 3, combining these pieces together. Our functions are not products, so we don't combine using the product rule. Our functions are quotients, so we combine them back together using the quotient rule. F prime times g minus f times g prime all over g squared. All right, and if we just plug those pieces in, we get to here, leaving all the factors as is. And this simplifies pretty quickly. Notice we can distribute the 2 through the parentheses and the 3 at the end through parentheses as well. And if you do that, notice you have a 6x that cancels out within the numerator. And then you can combine the 4 and the 9 together. Be careful with your signs, together as 13. Be careful. The quotient rule in the denominator for the answer for the derivative, there is g of x squared. So g of x here, the original function's denominator, is 3x plus 2. Our derivative, applying the quotient rule, has in its denominator 3x plus 2 squared. Okay, hopefully you're finding divide and conquer useful. It is a good approach very early on in calculus when you're getting introduced to the product rules and quotient rules. We're going to revisit divide and conquer when we get to the chain rule. That's the third and final very important differentiation rule within a few lectures, and we'll see how divide and conquer works there. All right, when you're ready, let's take a look at part B, which is only kind of a little bit more complicated than part A. Okay, so if you're interested, pause to make an attempt at this. Here, the derivatives are just slightly more complicated since we found the derivatives previously of f and g were 2 and 3, just constants. Here, the derivatives work out to contain x, just a little more work in simplifying. Pause the video and we'll check in maybe 2 minutes. All right, if you're ready, let's go through it. So we're going to apply divide and conquer. Remember, for the quotient rule, f of x, as we're using it, refers to the numerator, x squared minus 1, and g of x refers to the denominator, x squared plus 1. Again, standard notation for a calculus course. All right, we calculate the individual derivatives, which both coincidentally work out to 2x. I'll just to pause to give you a tip. Notice here, we see some of these 4 pieces, f, g, f prime, and g prime. 2 of them are the same. Now, if you see some of the pieces occurring in multiple spots here, both f prime and g prime are 2x, that's probably going to point to your derivative, your final answer, simplifying probably considerably. It doesn't always happen, but as soon as you see some of those pieces, f, g, f prime, or g prime, being the same, you might suspect that you get a very simple, simplified answer. So let's see that in action here. All right, we have our 4 pieces. We combine them using the quotient rule. So if our function is called y, we can express the derivative as dy over dx, Leibniz notation, or we can write it in prime notation as y prime. Both notations express the derivative of y with respect to x. Okay, and we're just applying a straightforward application of the quotient rule. The numerator is f prime times g, but minus f times g prime. And just be careful always to take g of x, the function's original denominator, and square that. Okay, now this end result could be simplified in several possible ways. You could just, brute force distribute, expand through the parentheses, and then, simplify, combine like terms that way. Once the problems start to get more complicated and look a little messier, there's a great technique here to simplify this very quickly. Notice, since both f prime and g prime are 2x, the numerator from the quotient rule, each term in the numerator has a factor of 2x. So instead of distributing everything and canceling and collecting like terms, let's just factor 2x out from the numerator. And that's, again, a very useful tip once the problems get more challenging and harder. Okay, so to go from the top to the bottom there, we're factoring 2x out from just the numerator. You're then left with x squared plus 1, and then minus, in parentheses, x squared minus 1. All right, and notice that simplifies very quickly. You can distribute that minus through the parentheses within the brackets. Your signs change, and then you can see the x squareds cancel out, leaving you with 2x, and then within the brackets, you get a factor of 2, that's 1 plus 1, and that just all simplifies 2x times 2. I'm pretty sure I checked using a very complicated algorithm before class. 2x times 2 is 4x. So we get our numerator 4x, and then the denominator x squared plus 1 squared. Okay, and that is it. There were a lot of tips in simplifying this. Again, it's one thing to know the statements for the product and quotient rules. Those are just easily memorizable or easily memorized. But it's another thing to be able to apply them efficiently. So again, think of maybe applying divide and conquer as you start some homework questions, and then very quickly you'll probably get the hang of how the product and quotient rules are used. We're going to pick up with some more complicated examples right after this in part 2 of this lecture.